So again, our whole goal here is to figure out how we can determine a change in entropy. We've just derived Gibbs' equation. Okay, we derived Gibbs' equation for a generic situation. We said, well, we could use this probably for ideal gases. So if I plug in, and let's just work with this one. Let's say ds. If I plug in for du, right, du, so ds is equal to c sub v dt over t. And then here I've got p over t, so I'm going to plug in plus r dv over v, because I know p over t is equal to r over v. Okay, so p over t is equal to r over v. Plug that in there. Here we go. Now, again, this is still a differential equation. Steve, I've not had differential equations yet. How do I do this? Okay, let's see if we can get it to an algebraic expression we can work with. What do we do? If we integrate this, right, if we integrate, let's just write that out, integrate from state 1 to 2. Why? Well, because a lot of times we're dealing with a process going from state 1 to 2. The inlet to the outlet of a steady flow control volume or a closed system undergoing a process. In either case, to go from state 1 to state 2, if I integrate both sides of this expression, I should get a useful equation. So integral of ds is just delta s. These are little s's. Again, back here, right here, divided by mass. Okay, so these are all lowercase values. So delta little s is going to be, I'm going to leave this term first, just because this is with respect to temperature. So I'm going to say from T1 to T2, C sub V dt over T. Plus, and then we'll go ahead and write this one out. You can skip some of the calculus here if you're comfortable with it, but I'm just going to go ahead and write it out. This one I'm integrating with respect to specific volumes, so it's from little v1 to little v2, r dv over v. Now let's focus on this first term. I'm sorry, on the second term. So S2 minus S1 is equal to, let's leave this first one alone, integral T1 to T2, C sub V dt over T, plus, and let's look at this term. What do we know about R? How does R vary as a function of specific volume? R is constant, right? R is constant, so it's going to come out of the integral. So it's R times the integral of dv over v from v1 to v2. Okay. So if we write that out, let's just isolate that and look at that. R integral v1 to v2 dv over v. Integral of dv over v, well, the integral of dx over x is the natural log of x, right? That's the antiderivative of dx over x. That's natural log. So this is the natural log of v. So this is R times the natural log of v2 minus r times the natural log of v1. And if you recall some of your logarithmic algebra, which if you're like me, you don't, you got to go look this up on Wikipedia or something like that, that's okay. There's a simplification we can apply that says if I've got natural log or log of any base, if I've got log of the same base, so I'm taking the difference of two logs of the same base, I can just say, well, that's that log times the ratio of the the log of the ratio of the arguments. Right? Natural log of v2 minus natural log of v1 is the natural log of v2 over v1. That's true for any log. Okay. So yeah, it's just one of those rules you have to remember. So what do we got then? Let's say S2 minus S1 is equal to the integral from T1 to T2 of C sub v dt over T plus R ln v2 over v1. Now what do we do with this guy? Well, remember when we first introduced specific heats for ideal gases, we said, hey, they're pretty constant, honestly. If you assume an average temperature and you use C sub v at the average temperature, you're going to get pretty close to the same estimate as you would if you assumed it was variable. That's true here also. If you assume, so this is an approximation, we can say S2 minus S1 is approximately equal to, if I assume C sub v is constant at the average temperature, then it comes out of the integral, and now I'm just integrating dt over t. Well, as we saw over here, that's just the natural log of t2 over t1 plus this other term, R ln V2 over V1. So this is the entropy change for an ideal gas. For ideal gas based on Gibbs equation. For ideal gases, this is one version of the equation. Okay, and that's using this side of it. Now remember, this is also equal to, we derived an enthalpy form, which is also equal to this form. And I'm not going to derive the expression, but we could do the same thing. I could plug in C sub P dt here, and I can plug in R over P there. Go through the same process we just went through here. I don't think you want to see that again. If you do, send me an email and I'll work it out for you. I'm not going to put that out for everybody. Let's just say similarly, I apologize if I spelled that wrong. Similarly, S2 minus S1 is let's say it's equal to, let's leave it as equal to the integral from T1 to T2 C sub P dt over T, and this one's minus, I'm just going to write R ln P2 over P1, because it's the integral of R dP over P. So it's R ln P2 over P1, and again, just like we did over there, what do we do with this integral? Well, if you assume this is constant at the average temperature, you can approximate this as C sub P at the average temperature times the natural log of T2 over T1 minus R times the natural log of P2 over P1. Now again, this is an approximation. We're using the average specific heat. Don't just pull the first specific heat at the lowest temperature. You actually have to go in and find the average specific heat at the average temperature. So go find the average temperature, go find the specific heat. This gets a little interesting if you don't know both temperatures. If you don't know both temperatures, you don't know the average temperature, and therefore you don't know the average specific heat. You can employ a guess and check method, an iterative process. We'll do that in the coming lectures. It's not hard. It does take a little bit of algebra. There's some other ways we can get around this, but again, Steve, what the heck are we doing here? Again, we're trying to find ways to determine delta S. Alright, so we find ways to determine delta S. We said one of those is tables, another one is the second law itself, and a third one is Gibbs equation. So if I have an ideal gas, Gibbs equation simplifies down to these two. This provides us delta S based on the properties we know for our substance. Okay? Alright, I apologize. I've got to send a text message real quick. I'll see if I can cut this out. Okay. So, where to from there? That's probably good, honestly. That's probably a good start. Well, you know what? I got a few minutes here. Let's talk about solids and liquids. This is for ideal gases. This is for solids and liquids. We can employ something pretty similar. Right? And so, if I've got a solids and liquids, ds is equal to du over t plus p dv over t. Well, what we do for solids and liquids is we say, well, this term essentially goes to zero because the change in specific volume based on pressure is pretty negligible. So I'm just left with this, ds is equal to du over t. And what we do is we say, well, employ the same logic. S2 minus S1 is approximately equal to, and again, in our text for solids and liquids, we use C sub P. So C sub P at the average temperature times the natural log of T2 over T1. Get you a really good approximation for the entropy change for solids and liquids. Again, to use a specific heat, important note, to use specific heats, phase must be constant. I would say be careful, but I'm just going to say avoid, for our purposes, avoid specific heats. Avoid specific heats for water in R134. I just can't write. Avoid water in R134. Unless you have water and you know it's going to stay, it's in the liquid phase and it's going to stay in the liquid phase. Or if you've got water that you know is in the vapor phase, you could use the ideal gas forms, but you've got property tables. It's a lot of work to go through to get S values for water R134 when you just go look up properties. Now, if you've got liquid R134 or liquid water and you know it's in the liquid phase at both states 1 and 2, this will get you pretty close. It'll get you just about as close as using the saturated liquid estimate that your text recommends. But if it's any other solid or liquid, some chunk of metal, some liquid that we know is going to stay liquid, or some chunk of solid is going to stay solid, this gets you a really good approximation for the entropy change. If it's an ideal gas, if I can get to the specific heat at the average temperature, this gets me a good approximation. Which one do I use? They're both okay. It just depends on, for a control volume, I probably know the pressures. For a closed system, I probably know the volumes, but you're not locked into that. As long as you know the pressures or you know the volumes, you could use either one. Okay? All right, that's probably enough for this lecture. That'll finish us up, and then lecture 19 and 20 are probably just going to be example problems. I'm going to look at the spring semester. I'm going to look at the spring semester. I've got videos there. I may just simply post those so they're already done and you've got them ahead. But I'll glance at those and see if they're appropriate. Okay, guys, that's what I got. Have a good week. Let me know what I can help you with. Okay, have a good one. Bye-bye.